Hello everyone. This video is about demo on Simufact Additive. So Simufact Additive is a distortion prediction simulation software for additive manufacturing, mainly for a powder bed additive manufacturing. So let's go and see the details of the simulation. So this is the initial page, launch page, where we can select a new project or we can open existing projects. So for this demo purpose, we'll have a new project. And I'll hit OK. So this is the introduction page where we have to select what is the type of process, and then the machines, and then type of a simulation that we want to run, and also the process steps. So before we go into the details of the process, first let me introduce you to the tabs that's available in the software. So first tab is for the selection of the machines and the process, and then the second one is to define the geometry, the CAD geometry of the part that we are going to print, and also to generate support structures. And the next one is the defining the process parameters, the printing parameters, and finally the last tab is for the FEA boundary conditions and the meshing details. So coming to the first tab, or the machine selection. So the first one is the process type. So in this demo, we are looking at powder bed fusion process. And then we have to select what is the type of a machine that we are using for this laser powder bed fusion. So most of the machine manufacturers list will be available as a predefined library. So all we have to do is select that specific machine. So in this example, we are taking M280 machine from EOS. So the moment we click, we select the machine, the print bed size gets updated to the machine's capability. And the next one is simulation configurations. So what type of a simulation that we are going to run. So basically there are three types: mechanical, thermal, and coupled thermomechanical. Mechanical simulation is mainly carried out for inherent strain type of problem, where it will be more useful in an industrial application where the process parameters and the materials are very much standardized, and they only rerun the simulation for a different geometry. If there is readily available inherent strains from the experiments, that can be directly loaded, and we can run the mechanical simulation. This is much faster. And for a research type of application, or any parameter exploration, or if you want to explore the influence of different process parameters, or like laser power, scanning speed, and then the layer thickness, powder compositions, then it's better to go for a thermomechanical simulation, which is a more detailed coupled analysis. This runs on the basis of multi-scale approach. And the next one is the sequence of steps. So the build step is nothing but a printing process, and then the immediate release step is the actually after the printing is complete, the part will be separated from the base plate. So that's called the immediate releasing, and then finally the support removal. So these steps are interchangeable. We can first remove the supports, and then finally the base plate can be separated out. Or we can even skip one of the steps. Like for example, we want to just print the part, and then see what happens when the support is separated out from the part, and we don't want to see what happens when we release the part from the base plate. So that can be deleted out. So only these two steps will be in the FEA model. So now we can see this environment is updated to the new machine's size. The next step would be to import the part. To do that, we click on the part, right click, and import. So I've already created a part in a different CAD package, and exported it as a STL file. So most of the problems we will be using a STL file, because the same STL file can be exported to the printing machine, and uh, same thing can be used, so that we know that there is no error, or a difference in the results caused due to the file formats. So the same file can be used for both printing as well as for the FEA. and the default location where the part gets loaded is on the corner. So it's recommended that we move it to the center, or the best practice would be to place it in the exact location where we will be having the actual printing part placed in the machine. And also make sure that we avoid all the mounting holes, or else it will create a problem during printing if we have already run the simulation. The next one is the support selection. So supports can be selected in two methods. One is we create the supports outside the Simufact environment, and then we import it into the Simufact. So this will be more helpful if we are generating our own custom supports, or we are developing the supports using some custom codes, or on complex lattice geometries. So then it will be helpful. Or else we can generate the support structure within the Simufact environment itself. So to do that, we have to just double click here. So it opens up to a support generation window. So first thing is critical angle. So critical angle is nothing but what is the minimum angle that support needs to be generated. So generic powder bed fusion approach is anything less than 45 degrees needs a support structure, and anything more than 45 degrees is self-supporting. So we are keeping the same as of now. And what is the type of method? So there are two methods in which we can generate. One is the Simufact's inbuilt support generation method, which has got very minimal controls. So we go for a second method, which is materialize environment. It's a third-party software which is being used in most of the powder bed fusion printers actually. So material is magic. What we do is we generate the STL file and we import it in material as magic software, and generate the support required support structures and create a slicings. So the same environment is better to generate the FEA model as well. So for this study, we are using a perforated block type support. So we have to define X and Y hashing, and then the rotation angles. And we will be using a perforation in our studies. So we also have to define what is the perforation parameters, mainly the perforation angle, then beam thickness and strut height, and also the finally the solid height near the bottom of the support, and as well as the top where the part it is going to get interfered with the part. So once we have defined all the parameters, all we have to do is just generate the supports. So now we can see this is the part, and support is generated beneath that. So once supports are generated, now we can just hit OK. And after that, we have to define the materials. So first is powder material. So most of the powders that is available in powder bed fusion technology, that is already listed in the library. So we can just directly click and select it. So for this example, we are taking Inconel 718 powder. And also we have to define the base plate materials that will also influence how much heat gets dissipated and what is the rate at which heat gets dissipated. So for the example, for this study, we had used 316, so we will use the same. And we cannot control the width and the length of the base plate. That is because it is defined by the machine's capability. So for a given machine, the plate is fixed, so we can only play with the thickness, and usually we keep it same as what manufacturer has supplied. So its standard is 30 thickness plate. If we change this plate thickness to study its influence on the heat transfer rates, then then the same thing has to be done in the printing as well. So we have to manufacture a new plate, and then we have to study it. So we don't usually don't change this parameter. So as we can see here, till now it was this tab was red, and now it has turned green, which means all when we update all the required parameters on the tab, it turns green and it allows us to go to the next tab. So here we define the build parameters. So for Inconel powder, 718 powder, we can define what is the standard process parameters. So for time being, I'll take 180 watts power and laser scanning speed as slightly lower, 900 mm. And these are standards. Efficiency beam width I've kept zero point 0.1 mm, and the layer thickness we had used 40 microns. So recoder time we can have slightly large. And scan rates, it can be estimated. So if we want to control it even further, you can have it inputted in a manual fashion as well. And from the thermal parameters, the initial powder temperature, then the chamber temperature, and also initial temperature of the powder bed. So we can also provide a preheating if needed. So in a to minimize distortions, usually preheating is done. So we can even add that into our model so that we get more realistic values. And also post build, if we want to mimic exactly what the operator would do, the screw unscrewing pattern. So how the unscrewing takes place. So the same thing can also be added into our simulation. Currently, I'll remove it to increase the speed of demo. Then comes support removal. So once we have all the printing completed and the base plate has been removed from the machine, we have to do the support removal from the part. So that we define here which are the supports that needs to be defined removed out. So once we have defined the process parameters, then finally it's the FEA's meshing size defining. So general thumb rule for Simufact simulation is the voxel size that we select is usually it should be such that there are minimum 2 voxels per any given minimum feature of size. For example, if we have a minimum wall thickness of 0.4 mm, then we need to have a voxel size of 0.2 mm so that at least there are 2 voxels for a given wall thickness. That's the thumb rule we follow. So here our minimum wall thickness was around 0.3 mm, but if we give half of that, that is 0.15 mm, the simulation time goes very high. So just for the demo purpose, I'll take a very large number. The disadvantage of having a very large number is we will not get the accuracy. So there will be a lot of errors in the model, and the distortions that the model predicts will not be close to the required result. But just for the demo purpose, we will go ahead with the larger mesh size. So to give you an example, if we use a 0.15 mm mesh size for such a small cantilever part, it will run close to 24 hours. So it is a computationally high demanding simulation. So now we have set all the required parameters. Now we can hit start button. So as we can see that there are a lot of warning and error messages that is coming, mainly because we have chosen a very large mesh size. This is one of the indication that if we get such warnings, our results will not be accurate. So it's better we go back to our meshing and redefine our mesh to make sure that we don't get such a warning and errors. Uh, then we hit start, and there are two types in which we can continue this start. One is direct start, where the simulation continues in the same environment, or you can put it on a queue. This is more useful when we are running multiple simulations or in a form of a DOE, and we don't want two simulations running in parallel, so that it does not load too much to the system performance. So since this is only one simulation now, I'll directly start. So the printing is in progress. So we can have different type of plots. This is a temperature plot. At the same time, we can have a displacement plot or even the stress plots. So we can first see the process of temperature plots. So I'll just drag the for a quick speed up process. So we can see that it's a we can see there is a repeated heating and cooling that is happening on each layers. This is one of the main reasons for the thermal gradient and residual stress built up on the parts, and finally the part starts distorting because of this repeated heating and cooling on each layers. So that we can see here. The same fashion, we can also see how the uh, stress built up takes place in each layer. So this is the below layers, and as we go higher and higher, how the stresses keeps developing on each layer because of the uh, previous layer being a little cooler than the top built layer, and then eventually getting cooled. So that we can see here. Same way, we can also see the displacement. The displacements may not be very high value at the initial stage, because displacements can be observed very drastically once the supports and the parts are separated out from the base plate. Now the part and the support will be held tightly to the base plate, so it will be anchored, so we can't see the right displacement values now. And also these values may not be an accurate value, because we haven't chosen the right mesh size. So this is much larger than what is recommended. So the values what we see are all not accurate ones. So now the printing is completed, and also the support has been removed. The part and the base plate is not separated, because in the first step we have deleted one of the process where we have direct immediate release. So that has been deleted. So we can see that even after the printing, the part and the support has been not separated. Uh, but this is just before the support removal. And this is a thermal plot, so you can see the same temperature everywhere after printing. Let's go to a displacement plot. So you can see here, so how it has varied after the after the plate has been removed. And this is the stress plot before and after support removal. Yeah, that's the update on the demo. Thank you.